Okay, so we're going to be talking about the fundamental theorem of algebra. Our example is going to be a little convoluted, not convoluted, but a little contrived. The fundamental theorem of algebra says that we can always represent any polynomial as the product of the variable minus its roots, or its real zeros. Now, if we have a graph, we can look at the graph and find its real zeros, or also known as its roots. Right here we have a root for this polynomial, and it is at -5. So that means if you put in -5 into this polynomial, it would go -5 plus 5, and this would go to 0, which would make this a root. So you have to change the sign of the x-intercept when you create this form of the polynomial. Now here I use a tilde instead of an equal sign because there's a proportional constant in this. I divided it by like 2,000 so it would fit on the graph. Here we have another intercept at -3, and this will create a 0 if we put -3 in here. And here we have a root at 0, and so when you have a root at 0, it's just going to be multiplied by x. Here crosses the x-axis at 0. Okay, so here we have one at 2. So 2 minus 2 is 0, and we have another one at 4. So the fundamental theorem says we can take any polynomial and multiply it by the variable time, or minus its root. The complication is that sometimes the root is not a real number, but a complex number. In that case, then the graph will not cross the x-axis, and you won't be able to find the root by graphing the function. So again, sometimes the roots are complex, and then you cannot find the root by graphing it. Also, the other complication is sometimes you can have a root of higher than one multiplicity. That means that if one of these terms were squared, let's say that the term was x plus 2 was squared, we would find the function reaching x minus 2 and then bouncing back up. So that would give it a multiplicity of higher than 1. Also of interest is the number of roots and the degree of the polynomial. This is a 6th degree polynomial, and you could find that if you did all this multiplication. And it has 6 real roots. Well, the fundamental theorem says the most roots of a polynomial, or the number of roots of a polynomial, is exactly the degree of the polynomial if you include the complex roots and the multiplicity of the real roots. So we can just count these directly. 1, 2, 3, 4, 5, 6. So we can figure out the degree of the polynomial in some cases by counting the number of x-intercepts. Also of interest is counting the number of local maxima and minima. Here we got one minimum, one maximum, one minimum, one maximum, one minimum. Those are called extrema, local extrema. There are 5 local extrema. There will generally be one less local extrema than the degree of the polynomial. Now that's not always the case, but that's the maximum number of extrema. Also, if we counted the number of inflection points where it changes concavity, here's an inflection point. Here's an inflection point. 1, 2, 3, 4. So I think it's 2 less than the degree of the polynomial. So that's some properties of polynomials that are associated with the fundamental theorem of algebra.